Welcome back to a new video about power electronics. In this example, we will discuss the flyback converter. First, we'll start with the theory and develop the required equations for our design. In the next section, we will then discuss how we can design a flyback converter from the specifications. Of course, we will see everything step by step in our calculations and verify these in MATLAB Simulink simulations. First, we start with the discussion of the transformer, because that is what we have in our flyback converter. This is the picture of a transformer. You see two windings. We have the turns at the primary side. It's also called the primary winding. And we have also the secondary part, which is also called the secondary winding. And this is in this case an iron core, but it can be also another material. You see here the source, which is then connected to this primary winding, and you have the load, which is then connected to this secondary winding. What you also see is that this is electrically isolated, so you don't see any electrical connection between these two wires. Now, of course, we need to look at the characteristics and use a symbol, and also develop the equivalent circuit to use that in our design. As said, this provides electrical isolation, which is very handy. And it produces step up or step down time varying voltages and currents at the output. That's the brief discussion of this transformer. So we'll see shortly the formulas also. There will be a relationship between the number of turns here in both windings here. The transformer symbols are as shown here. We have three in this case. It can be that you have an iron core as we have it here. So then you use a symbol like so, two vertical lines. It can be also an air core, so you don't have any connection like so that will be just an air. It can be also a special core like a ferrite core, so that then it's given by this dashed lines. What we will use is this model in the first case, and of course expand it to get it done for our flyback converter. You see the input here V1, the output V2, and the currents also I1 and I2. Now in this case, the primary voltage is given by V1 and the secondary voltage is then V2. So in this case, the voltage across this. And the current here is our primary current, and here the secondary current, I1 and I2 respectively. The N1 and N2 are the turns in the primary side and the turns in the secondary side. Most of the time we actually look at the ratio, not at the specific value, but you can of course also look at the values and then determine your ratio. There's a very important part, which is the winding orientation, because sometimes this goes wrong in some calculations. You see here two cases. We have the primary voltage, which has this winding. So here it comes from outside the paper and it goes inside the paper, and then make this turn and then goes back. But you can also make that similar here. In this case, then you are in phase with your input. So the output voltage V2 will be in phase with the input voltage or the primary voltage V1. But you can also have a different winding orientation, because we kept this primary orientation exact same. We look at it, you see here the difference between these two windings orientations. And then you will have a flipped version, which is then out of phase. So in this case, we have the phase shift of 0 between the output and the input. In this case, the phase shift will be 180 degrees, so it will be exactly out of phase. And we will actually use this configuration for our flyback converter. Okay. Now the necessary formulas for our discussion. The voltage ratio, which is then the output voltage divided by the input, so or secondary voltage divided by the primary voltage, will be secondary number of turns divided by the primary side number of turns. You see, actually, if you make this, let's say 20, you get 20 times larger voltage here than there. But you can also go down, so that there's actually the procedure from step up or step down for this transformer. The current ratio goes like so. So I2 over I1 is actually inverse the relationship. So it's actually not N2 over N1, but N1 over N2. And there's also a power balance. So because in ideal case, the input power or the primary power, P1, must be equal to the secondary power, P2. But we know P1 is V1 times I1, which is also equal to V2 times I2. Just a simple formula we know from power. But we can also rewrite this V2 as such. So we have now N2 over N1 times V1. And this will be then I2 is equal to N1 over N2 times I1. Now if I use these two equations and substitute that in here, you get this expression. Now the N2 and N2, they will cancel each other out, and N1 and N1 here also, so you will actually have here V1 times I1, that means exact same as the left side. So you see actually the proof that this is indeed correct, so power balance is here valid. Okay, let's go to the next part, which is about our model. We will use this, but we will now make a better model of that to use that in our flyback converter. And that's actually shown here. Of course, this is more complicated. You see here the R1, L1 and more components actually appearing. So let's go one by one. This is a practical transformer model, which is often used if you want more precise results. This part here is our ideal transformer, and then anything outside that is added to get it more close to the reality. R1 is our primary resistance and R2 is our secondary resistance. L1 is the primary inductance and the L2 is our secondary inductance. There will be also losses because of the core, that's the core resistance, RC, and we have also the magnetizing inductance here. Now, this parameter is very important because that is also the parameter we will use only in the design of the flyback converter. So the value of the Lm is very important and it will be used for our design of the flyback converter. The other 5 parameters actually we will just leave it and we only use this L sub m. Okay, now the flyback converter itself, you see here again the transformer. You see our DC input voltage, there is a switch here, there is this diode, capacitor and our load resistor R. This is the very simple flyback converter configuration. Now we can use this transformer model as we have discussed by adding only this Lm in our model. What you also see here is that the orientation here is different. That's also why we have this dot here. So you see here a dot at the primary side, which is V1. But the secondary side is actually flipped. That's actually what you see here, this dot. So where the dot is, that's actually where the current is leaving and where you have the positive part of your voltage. That's actually shown here. So this part in dashed pink area is our transformer model we will use for our flyback converter. And this is called the magnetizing inductance. Okay. Now we can look at 2 situations because we have the switch. If the switch is closed, that means this is a short. That's actually shown here. Now, if this is shorted, that means you have the voltage Vs across this magnetizing inductance, but also this primary side of your transformer. But if this is positive, that means this is also positive from bottom to top. Then the current will try to go like so, but we have here our diode, which will then be reverse biased, so it will be blocking. So it will be an open circuit. So there will be voltage between these 2 nodes, but there will be no current flowing in this branch. That's actually the reason for having I2 is 0 and there is an open circuit here. That's the situation first here. Since there's no current here, there'll be also no current there for I1 because the I2 is 0. So that means the IS here, the source current, is only the magnetizing inductance current that is not going through here. Well, in the second case, which is then the switch opened, that's actually shown here, so switch is going open. Then we have the power or the energy we have stored in our magnetizing inductance will be then released in this primary winding, because now this is open, so you can actually leave this left part of the circuit. That's gone, and this voltage here will be then equal to the voltage of the V2 times the N1 over N2. That's actually the relationship between the V1 and V2 we have discussed before. Well, we have of course V2, which is the minus of VO. We can actually see that because we measure from top to bottom, but we actually have this V2 flipped. That's actually why you see here V2 is equal to minus VO. And that goes to the primary side using this reflection of the N1 over N2 ratio. We also see that indeed the IS is 0, so that means the current here, which is our magnetizing inductance current, will be also flowing in this primary side. Okay, what you also see is the switch voltage here is equal to Vs plus the VO over times N1 over N2. Why? Because if you look at it, this voltage will be the voltage actually here plus the voltage here. But this is flipped, so it will be then minus of that one plus the Vs. That's actually why I have this expression for the switch voltage. Now the operation of the Flyback Converter is similar to the buck-boost converter we have discussed before. In summary, what's actually doing, switch closed, that's this situation, the energy is stored in our inductance Lm. Switch open, then the energy is transferred from Lm to the load, that's R. Okay, let's now go in the detail of the switching analysis that will allow us to design the circuit later and also develop our equations for our design. This is our Flyback Converter again in the switch closed mode. Now, if the switch is closed, you can see actually on the source side that we can write the following, because we have here the V1, which is also Vs, but it is also equal to the voltage across the Lm. That is of course given by the Lm times the time derivative of the current. That's actually shown here. This is of course the standard formula for the voltage across the inductor. We can rewrite this, so you can say, okay, I would like to have the expression for the time changing value of the current of Lm. That will be then Vs over Lm. That's actually shown here. Now, if I want to go to the delta changes, that means the delta of ILM, that will be then the delta T also, but that's the first part of the switch, which means it is the duty cycle times the switching period. That's actually this one. Now, if I now rewrite this like so, we have now an expression for the changing of the inductance current here as a function of the source voltage, duty cycle, the switching period, and also our magnetizing inductance Lm. Now, solving for the current of the transformer magnetizing inductance, we have actually this situation which says if the switch is closed, you have this expression for your changing current in your inductance Lm here. On the load side, we actually see the following. We can see the V2 is then equal to N2 over N1 times V1, because it just flipped, but it is of course the voltage is there, but there's no current there, so this is always valid. Okay, now let's go to the situation where you have the switch open. That's the second situation. Now, since the current of Lm cannot change instantaneously, that is the characteristic of an inductor, the current path must go also through the primary side. So it must be through like that. So you see this switch is open, so it means we don't have any connection here with our Vs. The stored energy in the Lm must go also through the primary side. So the current of this Lm enters the undotted region here, or undotted part of the primary side, and must exit the undotted part also from the secondary side. That's actually how the transformer works. So diode is now conducting because the current is leaving here at this node and going like so, and there is no anymore reverse biased diode. So the V1 is now equal to N1 over N2 times V2, and that's actually shown here. And since V2 is equal to minus VO, we already discussed that in the previous slide, we can take this together and we have now an expression of V1 is equal to minus VO over times N1 over N2. Well, we know that V1 is also the voltage across this Lm, which is, as we have given here, which is then Lm times the time derivative of the current through Lm. This is also shown here. Again, rewrite this, so you divide the right side by the Lm. That's actually the expression we see here, and then go to the delta changes. You see here delta of the current ILM, and this delta T will be then the second part of the switching, which is then the part 1 minus the duty cycle times the switching period. That's this, and that is now equal to this one. Now, if we now again solve this current for the situation of the switch open, then you have this expression you see here, indeed, that this is the expression we have if you multiply the left side and the right hand side by 1 minus d times t. Now we have two equations, or two expressions for our changing current of the inductor. Now when we bring them together, you see here now the switch closed and switched open conditions. We know from an inductor that the net change of the inductor current must be 0. So we can add these together and make that 0. So the summation of these two is 0. That means this plus that must be 0. Okay, I can now multiply by Lm left and right hand side, so I can leave that. That's actually shown here. And I have an expression here where I can use the VO and the VS and express that in terms of the duty cycle. This is really similar to the buck-boost converter. We only have here the N1 over N2 as an additional parameter. So solving for the VO, which is our load voltage or the output voltage, we have actually this expression. You see actually it's really similar to the buck-boost converter. And here again the N2 over N1. Now if you do this in a couple of steps, you will end up in this expression for your output voltage. Of course, you can rewrite this for the situation you get for the duty cycle. Very important note, we have different conduction modes. The first one we will discuss here, the continuous conduction mode or the continuous current mode. This formula is only valid for the continuous current mode. And that means your inductor current here is always above 0. The power balance says the following. The power from the source must be equal to power at the load. That's in ideal case true. So the average source current, so the average current of the source times the source voltage itself, that's the product, which is the PS, must be equal to voltage across the load, which is here VO, squared over the resistor. This is, by the way, the active power or the power we dissipate. So there is no dissipation on the capacitor, so that means you only take the resistor. Now the relationship between the average source current and the average magnetizing inductance current is given by this expression, which is actually pretty simple. So the IS, which is our average source current, must be then duty cycle times the average current of the magnetizing current here. So that means if I now use my power balance and the average current expression, we have now this expression. So you can replace this IS by D times ILM. And that's actually shown here. And now the average inductance current for this magnetizing part is then given by this. Now using the expression for the load voltage, which is here, because that's also shown here, we can now substitute this expression for the load voltage in this expression. You have actually, after a couple of steps, your expression like so. What do we see? Again, it depends on the duty cycle, it depends on your ratio, so turns ratio of your transformer, and also your resistor and your input voltage Vs. Okay. You can also have it in a different form because this can be also written like so. So you have the VO here and there's also the ratio here in a duty cycle and the resistor. So if you make your resistor larger, you can have your average current here smaller. And depending on the ratio, of course, you can control your average current of your magnetizing inductance. Okay, let's go up and then continue with the other parameters and other values for this current in the inductor, because we can also look at the maximum value of this inductor and the minimum. Well, the maximum value is the average current of the inductor plus the peak value of your changing inductor current divided by 2. And that was given by this expression. And similar form for the minimum inductor current, that is actually given by this, so you only use a minus sign here. So if I use this in here and using also this average inductor current formula, you get this expression for the maximum current, and for the minimum current you get that one. As I said before, for the continuous conduction mode or for continuous current mode, we require that our minimum inductor current must be 0. So it means we need to make that larger than 0. At the boundary, that means at the boundary between the continuous and the discontinuous current mode, we have that the minimum inductor current is exactly 0. So you can look at this equation and use that what you need to have for your parameter Lm. Now that's actually shown here. So we have this expression completely taking out and then equate that to 0, and you can now see that we can determine the value of Lm, which makes this continuous or discontinuous current mode operation. So I replace this to the right side and now also get it done here. So you see actually here this expression. Now because we lose a D, we lose D here, we lose the VS, we lose the VS, so you actually get this expression. We also know that the switching period is equal to the 1 over the switching frequency. So 1 over the switching frequency is equal to sampling period. That's the only change from going here to there. And when you also do this times that, will be equal to actually 1. So that's actually shown here. And now I would like to have an expression of Lm. I'm almost there. So 2 times the switching frequency times the Lm is equal to 1 times this, divided by this one, which is actually shown here. I can flip this. That's actually shown here, and also divide by the 2 times the switching frequency. That's all shown here. So this is an important formula, because we need to have our Lm larger than this value, which is also shown here, in order to stay in the continuous current mode. Okay. Another parameter is the ripple voltage, which is determined by the capacitor we have across our load. And that's given by this expression, similar to the converters we have discussed before. So you see the change in the output voltage, peak, divided by the average value of your output voltage is equal to the duty cycle over the RCF. And F is here again this switching frequency. Practical way to look at the ripple voltage is to look at the equivalent series resistance of our capacitor. So there is a capacitor resistance, which is our parasitic. That's given by this small letter r sub c. That will contribute significantly to this load voltage ripple peak. So the peak capacitor current is equal to the maximum diode current, which is also equal to the current on the secondary side of the transformer. So what you need to know about this situation is if the peak load voltage needs to be calculated, that is more exact or more precise if you use this value, which is then the peak capacitor current times the ESR, which is our equivalent series resistance of the capacitor, and that's also shown here. And you can also know that the maximum diode current or the peak capacitor current will be then also the maximum inductor current for this magnetizing inductance, and that's also shown here. Okay, let's now look at the waveforms in more detail for our flyback converter. This waveform is for the magnetizing inductance current. You see that it is staying above 0. That is also for continuous current mode operation. If that was, for example, going to some value and then reaches 0 and then stays at that 0 value, that will be a discontinuous current mode. So the analysis will be also a little bit different. This one is the IS, which is the source current waveform. Again, what we have for the continuous current mode. This is the diode current. This is the capacitor current. You see it is minimum value has minus the output voltage over the resistor. And this is the voltage V1, which is the primary voltage of the transformer. The maximum value is Vs. And the minimum value is minus the output voltage times the N1 over N2, which is the turns ratio in our transformer. Now again, this is the circuit. We see that here the source current and other parameters in this circuit. The average current is given by this, the maximum current by this, and the minimum current by that. So this is now a complete summary of the picture of the waveforms and the circuit and our important parameters and formulas. Okay, finally, let's go now to our design example of the flyback converter. We like to have a design having an input voltage of 40 volts Vs, and the output voltage or load voltage must be 15 volts, so it is a step down. And the output current must be 3 amps. So we have here the two values for our load. The maximum allowed peak output ripple voltage in percentage is here given as 6% or 0.06. Okay, how do we tackle this problem? Let's go one by one in the calculations. We first select our switching frequency for our switch here. In this case, I will select a 20 kHz, just a random value. Then I will start with the calculation of the output voltage or use the formula for the output voltage. This is now the formula we can use. We have also seen this in the previous discussion. You see the duty cycle and the ratio of the N2 and N1, which is the ratio of the transformer turns. And this is only valid again for continuous current mode. Now from there I can rewrite this and then get an expression for the duty cycle. So which is then again D is equal to 1 over the ratio source voltage divided by the output voltage times the N2 over N1 plus 1 here. Now we have here two unknowns because we see here the N2 and N1 unknown are unknown, but also the duty cycle is unknown. So we need to see what we can do in order to proceed here. So we can say if I want calculate this, I can select the N2 and N1 ratio. Now, for example, we can say, let's select this. So for example, I can do 1/4, so that means the N2 and N1 has a ratio 1:4. That means the following: the N4, I mean N1 is 4 times more, has 4 times more windings than N2. That's actually the meaning of this one. So then we have the following. We can now use that because this is 40 volts, this is 15 volts, this is the 1/4. And then you do the math, you get here exactly 0.6 or 60% of our duty cycle. So we know our duty cycle, that's step one. The load resistor is important, that is given from specifications in terms of the voltage and the current in the output. That is 15/3 is 5 ohms. And this is also the minimum allowed resistor, because if you reduce this, for example, 2 ohms or 3 ohms, then it will consume more current and then your voltage goes down. So that's of course not allowed. This is what we can use at minimum. The capacitor, that is important and that's related to that switching frequency and the duty cycle. And the resistor, so we can use this, and this ratio is given in the specification as 0.06. So you rewrite this, so the C expressed in the other parameters, you can actually see that 20 kilohertz for our switching frequency we have selected, the duty cycle we have calculated here 0.6, and the 0.06 from the specification, and the 5 ohm from the resistor we have calculated as the load resistor we can have minimum. That will result in 100 microfarads. This is also what we have as a minimum, so you can go above. So this was 150 or 200 micro, it doesn't matter. This is the minimum you need to have for this situation for the peak-to-peak output ripple voltage. So we select just this as minimum value 100 microfarad and we proceed. The magnetizing inductance is a very important parameter. The average magnetizing inductor current was given by this expression. We have discussed that before, and now we substitute here the values. We get here 1.875 amps. So you see we have now the values. And we can now select, this is a random selection, we can now select the peak, the current of this magnetizing inductor of a part of the average current of that inductor. So I take now here 64%, this is really a random value, of that current I have here, which result in 1.2 amps. You can of course go a little bit lower, maybe 0.2 or 0.5, depending on your application and the stress you want to put on your components. Now if I now use this value, peak value of the inductor current, and also the duty cycle and the input voltage and switching frequency using this formula, that will result in 1 millihenry for my magnetizing inductor. This is also the minimum, so we need to select this. You can go above, but this is what I want, and I want to have now also select this as 1 millihenry for this example. The maximum inductor current I can have is here calculated. I've already discussed that, so it is the average plus the peak over 2, that is then 2.475. The other one will be the average minus the peak over 2, that is then 1.275 amps. This is larger than 0, so it is indeed again a confirmation that this is a continuous current mode. We can check that also in a different way. You can use this formula we have discussed before in the previous slides about the LM value, which should be a minimum value, which is then given by this expression. We have taken here 1 millihenries, so let's see also that from this expression. 5 ohms, 1 minus 0.6 from our duty cycle, 2 times the 20 kilohertz, and here N1 over N2, which is of course 4. Why? Because the N2 over N1 was 1/4. Square that and you get actually here the 0.32 millihenries, which is indeed smaller than that one. So this is larger than the minimum value. So it is indeed again proof that this is in the continuous current mode. Well, let's also look at the source current value. The average source current is given by this formula. We already discussed that, duty cycle times the average current in this magnetizing inductance. So 0.6, which is our duty cycle, times the 1.875 amps from this average current in the inductance. That will result in 1.125 amps. Okay, let's now look at the Simulink circuit. So, and then discuss the results. This is the input voltage, 40 volts. Here is the transformer model, linear transformer, which is in this case given. And we have here the 1 and the 2, which is the ratio here. Not the ratio, I mean the primary and the secondary part. You see clearly that I have grounded this part here, so the current is actually leaving here, so which makes actually this 180 degrees phase shift. I have here my magnetizing inductance, which is 1 millihenry. I have here my switch, which is an ideal switch, and I give it using a pulse generator, a specific duty cycle, which should be then 60 degrees, 60% I mean. The diode and the capacitor and the resistor I have here also, and I also measure that here on the scope, and also give here the mean value of the inductor current of this magnetizing inductance, and also the average source current here using these blocks. What you see is the following. We have measured or calculated 1.875 amps for our average current of this inductor, and the source current average was 1.125 amps. So what do you see? Well, we see here really close values in the simulation, so it is 1.118 amps, so it is pretty close, and here 1.865 amps, so a small error, just a little bit smaller than what we have calculated, so we can say this is perfect. Okay, let's now go also to the transient response. This is now the plot. For the blue one is the source current, the pink one is the load voltage, and the green one is our load current. And this is the inductor current, or the magnetizing inductor current, ILM. You see here the pink, which is the load current, is approaching actually after this transient effect, after this overshoot, this 15 volts average. And the current is approaching this approximately 3 amps as we wanted. You see also that the inductor current here is also having this shape of overshoot and then stays actually above this 0 current, so that means it is indeed the continuous current mode. But let's zoom in this and see more in the steady state response. You see here again the values and the source current, the load voltage, load current, and our inductor current. These were the results for our inductor current, the average, the maximum, and the minimum value. You see here the minimum, which is 1.2634 amps, which is really close to what we see here. You see the maximum, it is 2.4634, which is also very close to that one. So that's really nice. You can also actually look at the average by taking the maximum and the minimum together and divide it by 2. That will result in 1.8634 amps, which is also very close to what we see here. Now for the load voltage, there was of course a specification of the peak output ripple. So let's see that. The maximum is here 15.37 approximately, and the minimum is 14.47. So if you use the exact values given here in the labels and add them up, divided by 2, that will be then of course the average, which is 14.92 volts, close to 15, so not exactly, but close to 15. And the peak value will be then here just the maximum minus the minimum, will be then 0.8949 volts. Well, the ratio here, which is of course maximum 0.06 as allowed, we can calculate that using the measured values from the simulation. That will result in 0.0599, so close to 0.06, again below that value, so it is indeed as we wanted. Alright, it was our example considering the design of a flyback converter. We have first discussed the theory and developed from there the design equations, and then built this circuit and verified this in MATLAB Simulink simulations. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.